My name is Craig Kennedy. I'm the Regional Sales Manager for Newterra's Decentralized Water and Wastewater Treatment Systems. I wanted to thank you for joining us this morning, and today we're going to be talking about an introduction and overview to vacuum collection systems. So their basic method of functioning, some of their benefits, and the types of projects where you may use them. So there are a number of different types of collection systems typical in North America. Traditionally, we would see gravity collection systems. So that's large diameter pipes at a steep grade with lift stations where required. Step systems, which are septic tank effluent pumped. So they have an septic tank that will remove a majority of the large solids and then pump through small bore diameter piping. Grinder pump systems, which don't remove the solids, they simply grind them up small enough that they can be transported through small bore piping in a pumped fashion. Steg systems, again, septic tank effluent gravity. So these would have septic tanks to remove solids and then smaller bore piping for gravity flow with lift stations where required, and then vacuum systems that we're going to be talking about today. Vacuum systems, though not very common, are definitely not new to North America. So earliest vacuum sewers were installed actually in 1892 in a suburb of Paris. The technology wasn't used widely in between then and around the 1960s when some Swedish engineers picked up the technology and made some improvements, and from there sort of grew in popularity in its application. So from a 2006 EPA document, there was more than 300 systems installed in the US in places like Florida, Indiana, Maryland, Virginia, New Mexico, and West Virginia. So not widespread in North America, but certainly not unheard of, and definitely have their advantages for some applications that we'll talk about. So an overview of the vacuum collection system. We have a home, an RV site, an office building, some generator of wastewater. The waste is going to flow by gravity from the source to a collection chamber. So inside that collection chamber is an actuation mechanism and a valve. So when water fills up the collection chamber, the valve is going to actuate and then expose the collection chamber to the vacuum that's being held on the entire network of piping. So you're connecting your individual collection chambers to the piping network, and that network is going to be sort of in a sawtooth pattern and in main lines and branches out to all of the different sites that you're connected to, all drawing back to number 5, which is your vacuum station. So in there you've got a pressure vessel that you're pulling a vacuum on, vacuum pumps to maintain that vacuum, and sewage pumps to transfer wastewater from the collection tank to the actual treatment. And you're discharging out to your treatment system. So zooming in on the collection chamber itself, we have influent wastewater coming from gravity or by gravity from a home or other wastewater producer. The water level will fill up to a certain point, and then the valve will be actuated. So in the Quavac vacuum flow system that Newterra represents, we use a mechanical float actuator to trigger that valve, but pressure transducers are used in some other systems as well. But basically, you just need something to tell the system, the water level has gotten to a certain point, so open the vacuum valve. So typically, the large diameter, 2 or 3 inch valve will be actuated by a small pilot valve. So it actually use the vacuum that's in the collection system piping to actuate that valve. So it's not an electrically actuated valve; it's a vacuum actuated valve. Once that valve is open, the bottom of the collection pipe there is exposed. Has water on one side and vacuum on the other. So the air pressure basically forces air and water up into that pipe, evacuating the chamber, and then the whole thing resets to be prepared for another cycle. So here's a quick video of that process. So you can see there's really good scouring velocity and high flows through here. So in terms of solids handling and keeping that network of piping clean, it's very, very high flows and high energy as things move through. So solids handling is of utmost concern in a sewage collection system. So different types of systems handle it in different ways. The step and steg systems obviously try and settle those solids out prior to getting into the collection piping. Grinder pumps will grind and macerate any solids. So the vacuum system has, again, as we saw in the previous video, really high scouring velocities. So it is designed to simply take the solids through the system and transport them all the way to the treatment. So here's a quick video here of intaking some large solids.
Yeah.
That's an industry standard diaper. And as you can see, the vacuum system and valve handles it with no issue. So after we pass from the collection system to the piping network, it's a little bit different than a gravity system or a force main system. So the piping will actually be installed in a bit of a sawtooth pattern. So that allows water to essentially sort of drain down to those low points and then be lifted up by the incoming air, as valves cycle. So again, air moving through the system is going to be our motive force bringing the water along. So this sawtooth pattern as well allows the system to overcome hills and rises as the water is sort of lifted up almost in like a sawtooth sort of ratchet type pattern. Here we'll see a video of that sawtooth piping in action as the air moving through the system is pushing the water along. So you can see before things started moving, the water essentially comes to rest in those low points of the sawtooth right before the shore rise, but never really fully fills up the pipe. So you still have the head space of the whole piping network essentially held at vacuum and interconnected, which will allow it to have the full force of that vacuum as it's overcoming those rises. Piping layout itself, when looking at a whole site, will be laid out in vacuum main lines and branch lines, and then direct connections to the actual specific vacuum chambers. So offers a good deal of flexibility when it comes to laying out the site, as well as having branch line valves in order to shut off specific areas of the collection system for maintenance or for troubleshooting or for shutting them off for seasonal operation, that sort of thing. And diameters of the pipe will obviously be of varying sizes depending on the flow that is going through that specific branch in order to minimize the vacuum loss throughout the system. Because with vacuum, you're only dealing with atmospheric pressure is your maximum. We can't crank up the available pressure any higher than that. So it's important to try and minimize losses throughout the system. So the piping network will typically be polyethylene pipe thermally welded from 4 to 10 inch diameter. Shallow trench installation, so we're not relying on gravity to move water through the system, we're relying on air. So really we just need to put the piping down below the frost line. And then it doesn't need to go any deeper than that other than the sort of the shallow sawtooth pattern that it needs to be installed in. So the air moving through keeps everything at high scouring velocities, high speed, and we can have main lines, 3-4 kilometers long, depending on terrain. That's sort of the extent where your pressure losses throughout the system start to come into play in terms of the maximum vacuum available and how far we can move water. The vacuum station is really the heart of the entire system. It's what's going to be maintaining vacuum on all of the piping network. And that's what actuates the valves. That's what moves the water through, is that the integrity of that vacuum. So typically it'll be a two-story structure or two-story construction with a collection tank and transfer pumps in the basement. So you'll come in directly from one or multiple main lines coming in from the distribution network, the piping network, into that collection tank. We're going to have vacuum pumps that are constantly keeping that tank at vacuum, and then sewage pumps that are transferring any wastewater collected in that tank up and out to treatment. Yeah, so we can see here, sort of bottom left is what one of these small vacuum stations may look like from the outside, and we've got some pretty typical centrifugal transfer pumps, steel pressure vessels, and then rotary claw vacuum pumps. Okay, so that summarizes essentially the overview of how the vacuum system works. So let's talk a little bit about the why, vacuum system advantages. So cost can be lower than, especially than a traditional gravity system. So we're using smaller diameter pipe. There's less excavations. The trenching is shallower and more narrow. Manholes aren't required, so that sawtooth pattern of the piping can give you a lot of flexibility to go over, under, around obstacles, and turn and without the need for a manhole to change direction. No lift stations, so we have the collection chambers, and then we have the vacuum station. Everything in between that is just piping. For really large installations, there could be multiple vacuum stations, but again, we can do a 3 or 4 kilometer run typically on flattish ground with a single station. The sewage moving through the collection system typically won't go septic. So because we're using air as our motive force, it's actually keeping the wastewater quite aerated throughout the collection system, so reduces odor and reduces potential for H2S gas hazards as well. The wastewater will be aerobic or at least not septic when it's hitting the actual treatment. So high pipe velocities prevent blockages, keep those pipes scoured clean. So it's less of a constant flow and more of a pulsed flow at high velocities as we get valve cycling and bringing air into the system. So moving that diaper right through the whole collection system from chamber to treatment. The system can also be easily emptied. This is a nice advantage for seasonal operations as well as areas that are prone to flooding. So if the system needs to be completely drained of water or is fully filled up with water, you can manually actuate the valves on the different collection chambers and sort of isolate things with branch valves and just slowly empty out the entire network of piping. So if it's a seasonal campground, you don't have to worry about that collection system freezing and being damaged over the winter if it's not being used. So no infiltration. So smaller treatment systems. At the end of the day, this whole network of PE pipe is going to be thermally welded and sealed because we're trying to maintain vacuum on it. So that means it'll be nice and tight regarding infiltration as well. And so also no water in, but no wastewater out either. So when you think of low pressure force main system, so a step or a grinder pump system, a leak in the lines would lead to raw wastewater being leaking into the environment. Where in this case, let's say someone's doing construction in their backyard and they put a shovel through one of the vacuum lines, or they're somehow damaged in another way. We're actually not going to get wastewater leaking out into the environment. We're going to be pulling air and potentially groundwater into the system. So it's really quite responsible from an environmental perspective. And then there's a reserve volume built in at each home or each 4 homes in case of power outages. There's some volume in that tank that can be used. As well, power outages aren't necessarily an issue because you don't need power at the collection chambers. It's all mechanically actuated valves that are using the vacuum in the actual system or in the actual collection piping. So if you have backup power at your vacuum station, you essentially are powering your whole collection system. So considering some of the advantages that we talked about on the last slide, there's sort of certain parameters that make vacuum systems, good fit for a project. So if it's replacement of failing septic systems, so a bunch of existing homes that are being brought onto a new treatment system, perhaps, the vacuum valves could actually be installed directly into the existing septic systems, and then just evacuate those chambers from there and be connected to the collection system that way. Areas with high water tables, so whether it's an island or a coastal community, an RV park on the lake, things of that nature, the vacuum systems are really well suited for these. So we have low depth of installation for the piping, so we can stay above potentially high water tables. Lower construction cost in general in these high water tables because we're smaller diameter piping and putting it lower. As well, the sort of flood-proof nature of the collection systems is nice as well. If these things flood up, we can just evacuate the whole system sort of chamber by chamber and reset things back to normal. Areas with constraints around deeper construction, so high bedrock, if there's existing homes or existing infrastructure and roads and things like that, the sort of smaller diameter pipe, just underneath the frost line, means that we can be a lot more nimble with installation in with existing homes or existing roads and things like that, as well as we don't need to blast through bedrock to get really deep sewer systems. We can stick pretty close to the surface. Flat and rolling terrain. This would be a challenge for gravity sewer systems. You would end up with a lot of lift stations over extended areas of flat or rises in the terrain. But this is ideal for a vacuum system. So that sawtooth pattern basically just keeps the water moving, across flat terrain because we're using air instead of gravity, and can go uphill and then back downhill on the other side. Environmentally sensitive locations, or where the really environmentally protected areas. It's where pulling a vacuum versus pushing sewage means that any breaches in the line will be sucking in water and air rather than spewing untreated wastewater into the environment. And for new urban development or rural areas, connecting up to a vacuum system versus gravity, we've seen you could expect 30% reduction in cost versus a gravity system, and when you're comparing it to grinder pumps or step or steg, a lot less maintenance on a per home basis, because we have a little mechanical valve versus submersible pumps for every home. So on a maintenance level, the more you can minimize pumps, the better. So all of our pumps are really sort of centralized just at the vacuum station or rises in the terrain, but this is ideal for a vacuum system. So that saw and can go uphill and then back downhill on the other side. Environmentally sensitive locations, or where the really environmentally protected areas. It's where pulling a vacuum versus pushing sewage means that any breaches in the line will be sucking in water and air rather than spewing untreated wastewater into the environment. And for new urban development or rural areas, connecting up to a vacuum system versus gravity, we've seen you could expect 30% reduction in cost versus a gravity system, and when you're comparing it to grinder pumps or step or steg, a lot less maintenance on a per home basis, because we have a little mechanical valve versus submersible pumps for every home. So on a maintenance level, the more you can minimize pumps, the better. So all of our pumps are really sort of centralized just at the vacuum station. Yes, thank you very much. That's a preliminary introduction to vacuum collection systems, some of the benefits, some of the applications of where you might want to use them. I hope you enjoyed. I hope you learned some things, and we'll stick around for a little bit to answer any questions you have. Thank you very much. Okay, I don't see any questions in the public chat there, so if you have any, feel free to put them there. I did get some through on the private. Issues around flooding and during a hurricane potentially. Is our system able to cope with that, and why? So in terms of flooding, one of the nice things about the Quavac system is that the actuation of the valves is mechanical, rather than some other systems can use sort of a pressure transducer tube with a spout that comes up that can potentially clog or be fouled, and if it's fully submerged, that can have an adverse effect on that. The mechanical system is nice and robust in terms of flooding. As soon as they start the system back up and pull a vacuum, those chambers will start to drain. Noise from vacuum stations. Yeah, so there are some the vacuum blowers in the actual station itself that would be they're probably up running at 80 decibels or somewhere around there on the actual blower. So you can attenuate that obviously either with blower sound attenuation around the blower itself or in the actual building that those blowers are housed. In terms of contractors installing piping, that's sort of our MO in terms of go-to-market in North America. So we're not general contractors. So we would supply designs and the collection chambers and equipment and all that. But it would be about partnering with local contractors to do the actual excavations, installations of piping. And that sort of thing. Range of pressure that the vacuum pressure valve will operate. In terms of the actual operation of how much pressure is required to actuate that valve, I'm not sure. The actual vacuum tank itself is usually held at 0.4 to 0.6 bar. And then the further you go out into the system, the further along those sort of trunk and branch lines out to the individual chambers, there will be reduction throughout there from pressure losses. So I'm not sure at the end of the line what the actual minimum is, but we definitely take that into consideration when we do the design. That's really what sort of limits the number of or length of branch lines and pipe sizing and whatnot, is that vacuum loss throughout the system. Another question, how large of a vacuum is required for these systems? So actually just answered that one and the one above. 0.4 to 0.6 bar is what we hold the vacuum tank at. Michael Emmond asks, what is the extent of Newterra offering? Do you offer the network design? Yes, so we would provide the engineering, including pipe sizing, vacuum losses throughout the system, sizing of all that, looking at site layouts and locating, the number of collection chambers per home or per unit, as well as supplying the collection chambers network isolation valves, and then the equipment for the vacuum station itself. Brandon Keller asks, how many Sawtooths would you need on over 400 or 500 foot length, say on a 4-inch line main? Let me just bring that up. So typically, the length between Sawtooths would be 40 to 60 meters as a typical length. Ken Sayback asks, is there a new Terra contact we can get a hold of for product info? Yeah, that would be myself. For Ontario and Canada, I would be the primary contact. And then for in the US, it would be my counterpart down there, Marshall Dean. Not sure if you can see my contact info on here, but my email is, let me just, as the email for myself for any inquiries in Canada. And then for anything in the US, it would be Marshall Dean would be the best person to get in touch with there. Often also get questions about freezing temperatures and cold climates, and sort of how the vacuum installation works there. And do we need to put everything below the frost line, or is it fine to be above? So typically the install with that would be the chamber, and the vacuum line going from the chamber to the branch or the trunk line. Those can be above the frost line. So that initial sort of from chamber to branch line is constantly going to be empty and evacuated of any water. So there's no risk of freezing in that length of pipe. And then the chamber itself, will be sort of set down into the ground somewhat, and constantly has sort of new wastewater flowing in. So it isn't at a high risk of freezing. For really cold temperatures, you can add some insulation in and around that chamber as well to further protect. Ken Saybeck asks, what is your primary target for this technology? So I think what the best application for this are, or the best types of applications are, either new builds or retrofits of RV parks, campgrounds, things of that nature are really a really great application for this technology, as well as small to sort of medium-sized housing developments that may be in challenging environments of some sort. So whether that means that they are have high water tables or poor soil or high bedrock. Or just rolling terrain that would make it a challenge to apply a gravity system. Pretty much anywhere where you'd look to an alternative collection system, anywhere where you'd be looking at a grinder pump, force main system, or a stagger step system, vacuum could also be a potential solution. Okay, that looks like that's the last of the questions coming in there. So if no one has anything else, thank you all very much for your time. And if you need any further information, please feel free to reach out to me. We also have a handout here. You should be able to, up at the top, sort of right where it says, chat, Q&A, polls. There should also be handouts, so you can download the brochure sheet for our vacuum system. And just do one final check here. I think if that's all, thank you all very much for coming, and have a great rest of your day.